Okay. What's going on with this thing? Anyway, sorry for the disruptions. Somehow I'm not. I'll figure it out later, maybe. Anyway, yeah. So this is a follow up on Arvin Ash's response to me. So I'm gonna have to get into it right away because I'm on call and I just got called. So whenever they come to get me, I gotta go. But anyways,
This video is brought to you by Brilliant. Click the link in the description to sign up for free and support this channel.
so this
What's the
is
most important concept in physics?
Arvin,
Quantum mechanics?
Arvin Ash.
I would argue that it's space-time. Without it, we would have no stage for all the physics we know of to act on. It would be like an artist with all colors of paints, brushes in all shapes and sizes, but nothing to paint on. And so there would be no masterpiece. Just like an artist is nothing without a canvas, or an actor is just another person without a stage.
I don't know what he's talking about. He's talking about whatever he's talking about. But anyways, he responded to me. So you can watch the video and tell me something if you want. But these are the responses that I had, and the last response I had was, let me see, particles can have energy with no rest mass. For example, photons. That's his last response to me. Right. To begin with, I said time and distance depends on what? Mass. So he's talking about a particle with no mass or no rest mass. For example, photons. So I say, yeah, they're emitted from a mass, and they also experience no time or distance. They also experience no time or distance anyway. So what are you talking about? You're talking about something totally unrelated, right? And this guy here is way out there. It's like I don't know what universe he's from, but he's like way out there. For example, look at this. Oh, where'd he go? So I responded back and forth a couple of times, trying to, bring him in. Trying to bring him into, here, look what he says. Time cannot be slowed down. So he's like way out, way out. I don't know where he is. I don't know where he is. He's way out somewhere. And then he gives us, I didn't even read the nonsense, but, if you say one thing stupid, then I'm out of here. Time cannot be so, you know, he's way, he's gone. He's, somewhere in La La Land. But as far as uh, Arvin Ash is concerned, the last thing he said to Jungle Jargon was particles can have energy with no rest mass, for example, photons. And I said, you know, I said, yeah, they're emitted from a mass. They come from a mass, and they don't experience any time or distance anyway. So what do what's that got to do with the price of rice in China or beans in Mesopotamia or whatever? Anyway, just an update, quick update, because he never answered me back. And I said, yeah, they're emitted from a mass. They come from a mass, and they don't experience any time and distance. So what are you talking about? The particles can have energy with no rest. Yeah. Example, photons. Yeah. Yeah, but I'm talking about, this is what I'm talking about. I'm talking about mass. Mass is what slows down time and contracts distance. If you don't have any mass, you're not going to slow down time or contract distance. So what are you talking about particles for? So what's that got to do, with anything? It doesn't have to do anything. This is one of the greatest scientists, ever. And he wants to question me, because what I said initially. It's what I said initially. I said, space time wouldn't even exist without matter, right? So he comes along and said, he didn't even respond me, directly to me the first time. He says, that's not what general relativity says, right? You know, this is a scientist, for crying out loud. This is one of the greatest scientists in the world. And he's, promoter of sciences or whatever. The space time wouldn't exist without matter. And he says, no, that's not what general relativity says. Space time, there's his claim again, would exist. How? And it would still bend. It would still bend if there was any energy, right? Matter and energy bends. Right. But that's what I'm saying. It's like, how are you going to have space time without matter or energy, which matter is energy? And where's the energy coming from anyways to begin with? You got matter. Yeah, we got matter, but it's here, it's energy, but we don't see any energy. We don't see any energy being added to the system right now. Energy was cut off from us. We're cut off. We're cut off from energy. We're dead. We're dead. We're cut off from the power. I mean, that's the observation. That's what the observation is. We're cut off from all the power and the energy and everything. He says, if there was energy, space. But there is no energy, appear from nowhere, and the only energy there is matter, which bends space time, right? I mean, this is the greatest scientist in the world, right? So what does he come back with? I said, my answer to whatever, what does he come back with? He says, particles have energy, yeah, a small amount of energy, with no mass. I'm talking about mass. You have to have particles are going to dilate time and space. This is a scientist. This is a scientist. This is one of the. I mean, this is he went through all the schools. And I came from the Amazon jungle. This guy went through all the schools and everything, and this is what he comes back with me to say. He's talking about small amounts of energy with with no mass. I'm talking about mass. He's talking about small amounts of energy with no mass. That was the last thing he said. Just an update. That's about it. And sorry I can't, hang around or anything, but we have to call these people out. I was going to name the title "Calling Out Arvin or whatever, but maybe I'll change it or whatever.
We must have some place for physics to unfold. That place is space-time. At one time, space was thought to be nothing, just an empty void, a vacuum with no matter in it.
This is the worst thing ever. Space-time was thought to be an empty void. This is what Lawrence Krauss said too. Because the Bible said in Genesis, the Bible says the earth was formless and void. But it's talking about the earth. It's not talking about space. The earth was formless and void. Yeah. That means there was no particular, intent or purpose or anything going on. And it was no living organisms, right? That's what the void means. The earth was already created. It doesn't mean that the earth wasn't there. It doesn't mean the stars weren't there. It doesn't mean the sun wasn't there. It means the earth was formless, didn't have any particular form, and then it was void of life, of anything by intended purpose. And then they extrapolate that, the Bible says the universe is void or something. They got this thing in their mind, if you want to be a scientist.
Then in 1908, Hermann Minkowski came up with the idea that time could be thought of as a fourth dimension, along with the three dimensions of space. And Einstein later showed that the space-time is a kind of geometry that can bend and contort, affecting the trajectory and passage of time for objects. We take it for granted because it's all around us, ever present, like a fish takes for granted the water it swims in. But what is this thing all around us, this all-important existential canvas without which the universe and we would not exist? And how can space and time be part of the same canvas? Space is measured in meters and feet, while time is measured in seconds and minutes. How are the two seemingly interchangeable? This seems to make no sense. And why do we...
But not necessarily interchangeable in our universe. Maybe if you want to extrapolate the mathematics and go through a black hole, then you're going to switch time and space. But otherwise, it's not interchangeable.
We only have one dimension of time and three dimensions of space. Why not 2, 4, or 5 spatial dimensions and more than one time dimension? I'm going to attempt to explain this intuitively. Stay tuned because you won't want to miss this. That's coming up right now.
You don't want to miss this.
The definition of space-time is the set of all points in space and time located with 4 numbers. This would be the location in three-dimensional space, X, Y, and Z, and a time. You can also call these events. So if you had an event where you were meeting someone, you might say something like, I'll meet you in the building on the corner of 5th Avenue and Broadway on the 6th floor. And of course, you would have to tell them what time. Otherwise, the meeting might not take place. The problem is not in understanding what space and time are. We can intuitively understand the 3 dimensions of space. It's all around us. We can move front and back, left and right, up and down. And we can understand time by the ticks of our clocks and changes that we can observe over time. But the problem is in understanding how these two seemingly completely different concepts can be combined into a 4-dimensional continuum called space-time. This is not intuitive at all. Space is measured in meters and feet. Time is measured in seconds and minutes, etc. These seem to be 2 completely different things. How can distance and time be interchangeable? And how can both be part of the same thing? In order to understand this question intuitively, let's compare the geometry of space-time with the geometry of space, since space is something we experience every day and can identify with. For simplicity, let's look at only 2 spatial dimensions. Note that what I'll show here works for 3 dimensions too, but the math is more complex. In ordinary Euclidean space, the distance between 2 points A and B is fairly simple to figure out. All we need to know is the coordinates in the X and Y direction. Knowing this, we can use the Pythagorean theorem to do some simple math. X squared plus y squared equals z squared. The distance z is the shortest path from A to B. And it's obvious that any other path from A to B will be longer. So for example, if we take a curved path or a zigzag path from A to B, that path is going to be longer than z. That's simple enough. Now let's look at space-time. In order to make this as similar to the 2D model as possible, let's again use two dimensions. But this time we'll use one spatial dimension, x, and the other dimension will be time, t. This time, A and B are not just points in space, but also time. So you can think of them as events rather than simply points. The math that we have to use here is not based on Euclidean geometry, but Minkowskian geometry. There are some big differences. The line between A and B does not represent distance, but time elapsed between the two events. We'll call this elapsed time E. A straight line represents traveling at a constant velocity between the two events. You might say, well, to figure out the time elapsed, all I have to do is subtract the time I left at A.
Constant velocity, right? The speed of light is a constant velocity. Einstein drilled into everybody's brain that the speed of light is constant. It doesn't change. Except the measures of time and distance do change, which changes the speed of light. Oh my, like, what is wrong with you people? What is wrong with you people? Speed of light is constant. Using the measures of time and distance, the speed of light is constant. Absolutely. But what happens if the time speeds up and distance gets bigger? You're going to change the speed of light, which I've been trying to explain to people for a long time.
A from the time I arrived at B. Isn't that the elapsed time? This is where the ideas of space-time and special relativity take an unintuitive turn. The answer is no. You can't subtract the time you left from the time you arrived to find the elapsed time. Why? Because you have to remember the time is relative. Unlike Newton, who thought
relative to, time is relative, distance is relative, which alters the speed of light is what I'm trying to explain.
Time was absolute. Einstein showed that it was not. Newton was wrong about this. Einstein was right. Ticks of the clock change with velocity. Time flows differently for anyone moving with the speed compared to someone standing still. So this elapsed time will be different because traveling from A to B requires a velocity in space. If someone was simply standing at A, moving only in time but not in space, then yes, you could just subtract the time difference between A and B and get the elapsed time. But not in the case where there was traveling in space involved in order to get from A to B. Given what I just said, you'd be correct to presume that the Pythagorean theorem could not work here. So x squared plus t squared is indeed not equal to e squared. The formula that works here is actually only slightly different, and it's this. E, or the elapsed time or duration, squared is equal to t squared minus x squared. The minus sign makes a huge difference. Essentially, what this formula shows is that the more one travels in space, represented by x here, in any given amount of time, the shorter the elapsed time. Time and space seem to have a kind of inverse relationship. So while in Euclidean space, a straight line is the shortest distance, in Minkowskian space-time, the line between A and B is the longest duration. The more you move in space, the less you move in time. And the less you move in space, the more you move in time.
Yeah, but he's talking about special relativity. He's not talking about general relativity right now. If you're talking about speed, you're talking about special relativity. If you're talking about, gravity, you're talking about general relativity. But since things are moving anyways, and who knows how fast the sun is moving or the earth is moving around the sun, and the sun is moving around the galaxy, who knows how fast that is. And who knows how fast the galaxy is moving. That's all going to affect the measure of time and distance. So you have to consider all these things to understand what's going on. And, it's got nothing to do with Euclidean or Minkowski or nothing. It's just you got to do all the math to figure out, how fast is the sun moving around the galaxy, and how fast is the galaxy moving around other gravitational forces. You don't know. I mean, at least not easily, but you have to take all that into consideration to determine the measure of time and distance. But once you leave a galaxy, you got no matter to slow down time or distance, which changes the speed of light relative to our measure of time and distance. It's not that complicated. It's not complicated.
So, for example, in space-time, if you took a curved path from event A to event B, or a zigzag path, then the elapsed time would be lower compared to a straight line between A and B, because you will have traveled more in space than in time. This can be seen in the equation we saw earlier, but we can also illustrate it with a simple example. Let's say you had a twin brother or sister who stayed on Earth, while you traveled to a far distance in space at some speed, and then back to Earth. You will have aged less because you would have traveled more in space during the same time that your twin stayed on Earth. Less time would have elapsed for you than your twin. Now, I'm guessing you have a lot of questions, so let's address some of them. First, you might ask, where does this formula come from? It comes from Minkowski. For only 2 dimensions, the math is not that difficult, and I have a link in the description if you want to know how it's derived. Another question you may have is, what's the difference between the time duration E and T, the time coordinate? So E, the time duration, would be what the person traveling from A to B would measure on their wristwatch or clock. Little t is the time coordinate of the system. This is like a universal time. Now, such a time doesn't really exist. It's a human invention.
No. There's no universal time in the universe. There's no single measure of time in the universe. Get that into your head. There's no single measure of time or distance anywhere in the universe. You don't have a fixed measure of time. But anyways, he might be trying to debunk him or whatever. I don't know.
But if it helps, you can think of this as the time measured by someone standing perfectly still in the universe. In Newtonian physics before relativity, the time coordinate t and e, the elapsed time, were thought to be exactly the same.
Yeah.
This is the outdated concept of absolute time. Einstein showed that there's no such thing as absolute time. And so that's why we have a new formulation. Now, perhaps the biggest question you might have is, how the heck do you add time and distance together, since the units are completely different, meters versus seconds? Well, this is a great question, and it's what I've been working to get to. The key is that there's an important conversion factor between time and space that allows us to convert one to the other. And that
time and space, time and distance?
That conversion factor is, drum roll please, the maximum speed limit of the universe. And that speed limit, as far as we know, is the speed.
There you go. The speed limit is 186,000 miles a second, or close to 300,000 or whatever meters per second. And what if the time change? What if the rate of time changes? What if time speeds up, and what if distance expands with no matter? That means light from distant galaxies is going to arrive much faster than with our rate of time and distance, our measures of time and distance. Because we exist in a contracted distance and slowed down rate of time, That's because we're inside of the Milky Way galaxy, right? So we have a slowed down rate of time and a contracted measured distance, a smaller measure of distance. But if you want to extrapolate into outer space, there's no matter to slow down time and there's no matter to contract distance. So the distance of 1 meter is going to be like big. Hold on a second. I got to answer my
speed of light. The speed of light.
Hold on. Okay. All right. Bye-bye. Well, it's a good thing. My boss just called and said everything's good. We're going to do it in the morning. We're not going to do it right now because he had to go do something. There's Dan Straight. Look at that. Alex Cox. Alec Cox. Let's see. What him say? How is it that they can even measure anything? Because nothing just did nothing. It's like, yeah, how do they know what to measure? I mean, especially with all, I mean, how do they know what the measure of time and distance is? They don't. But they're talking about they're talking about they're trying to say a single measure of time and distance. Doesn't make no sense. This is why we got to call them out. We got to call them out. So this is why I'm calling out Arvin Ash. Not because of him, because I don't dislike Arvin Ash, but because of the teaching, all the teaching. And we got Dan Straight. What did he say? He says the idea that we would still see a star that exploded 1,000 years ago is false. Yeah, especially when you don't know the rate of time or the measure of distance. I mean, they're guessing. They're guessing. They don't know. They don't know what the things are. Okay, meters aren't even correct measurement. Metric system from the equator to the poles, feet, and 3 feet. Well, it's meters, almost 3 feet or whatever. It doesn't matter what measure that you choose, a standard of measure. We could use like the measurement to make the arc. The distance from your elbow to the tip of your finger. It doesn't matter what measure you use. That measure is going to be, if you go away from matter, it's going to be huge. So if you go into outer space, you're going to be huge. You're going to be big. You're going to be big. And then time is going to go by much faster in outer space. You go into outer space away from matter, the time is not going to be 1,001. It's going to be 1,001. So, I mean, that's the reason we are able to see distant starlight, because these people, I wonder about their IQ. I always wonder about their IQ all the time. It's like, if you turn your flashlight on in space, it doesn't travel after you turn it off like a laser gun in movies. Turn the flashlight on. Doesn't travel after it. Oh, I guess I can see what Dan is trying to say. Is like when you turn it off, it turns off. You know, I mean, relatively speaking, yeah. I was like, you turn it off, it's going to be off. You know, but the light that you beam out is going to keep on traveling, but it's going to turn. I mean, it's going to turn off when you turn it off. Whatever. But actually, let me think about that. We got a shorter measure of time with this. I don't know. I'll think about it later. Thought experiments. You got to do the thought experiments. Okay. Anyway, let me get back to the video since I don't have to go to work right now. Try again.
1,458 meters per second. As you know, speed is distance over time. If we multiply this speed by time, we get a distance.
That's meters per
so
second.
Now we can convert time in the same equation as distance.
No, don't confuse. Don't confuse everything. He's trying to switch distance and time and time. The only way you can switch them is if you go beyond the black hole, which you can't do. That's a mathematical construct. If you go beyond a black hole, time becomes distance. Distance becomes time. But that's like a mathematical construct. It's not reality. And they keep on talking about a whole bunch of stuff.
Equals c times t. Thus, the equation works by using this conversion factor. And note that this speed can also be written more conveniently as 1 light second per second. So converting all the distances to light seconds instead of meters can make it easier with the math when using seconds and meters for our units. Now let's go back to the graph and look at some of its profound implications.
1 light second, but wait a minute. Isn't your second changing its rate of time? Isn't the second getting faster in outer space? With no time, with no matter to slow down time or distance, isn't the second going to be a lot faster? It's like why are you using a second to measure anything? You can't use a second to measure anything because it changes as soon as you leave the galaxy. It's a different measure of second. I mean, a second is going to be like I said, it's going to be faster, much faster. It could be or whatever, maybe even faster than that, because there's no between here and there's no matter to slow down time. So how do you even know what the measure of a second is? It's like these people. I mean, I hate to keep talking about their IQ, but these people, man, these people. I mean, you gotta think. You gotta do the thought experiment. If you don't do the thought experiment, you're not going to understand what's going on, because the measure of the second is never the same. If you get away from a galaxy, the measure of a second is going to be like almost instantaneous. Besides the measure of distance, which is going to be greatly expanded. So if it's greatly expanded and the time is going faster, 186,000 miles a second or 300 meters per second or whatever it is, 300, what was it, 300, whatever it is, 186,000 miles a second. I'm in America, and I'm old school. 186,000 miles. The mile is going to get bigger. The mile's not going to be contracted like it is inside of a galaxy. The mile's going to get bigger, and the time is going faster. So you're going, I mean, where's your Where's your IQ? Where is your IQ? That's what I keep asking these people. These, whoever it is, physicists, cosmologists, or whatever. Where is your IQ? Where is your IQ? I'm from the Amazon jungle, for crying out loud, and I can understand general relativity is like run around circles around you.
This simple formulation for a two-dimensional space-time can be extended to the real four-dimensional space-time we live in. And that four-dimensional geometry is the foundation for understanding general relativity, with the addition that the space-time is no longer flat, but can curve and contort. So the math gets pretty complicated pretty quickly in general relativity. But one of the consequences of a curving space-time is that this results in the phenomenon of gravity. Gravity also results in time dilation. That is, time runs slightly slower for objects close to massive bodies like the Earth, where gravity is higher, compared to those far away in space. But this time dilation effect due to gravity is weaker on relatively low mass objects like Earth than the time dilation effect due to high velocities. Space-time is a four-dimensional stage for physics to take place, and it has existential importance. You might ask, well, why do we have only 3 dimensions? Why not 4 or 5 or 6 or more spatial dimensions? And while we're at it, why not more than one time dimension? Well, first of all, additional large spatial dimensions probably don't exist because we would have detected them if they did. And more than one dimension of time could result in closed time-like loops. In other words, it would allow travel to the past. This is considered an impossibility because it would break causality. So, for example, it would allow you to travel to the past and kill your father, such that you would have never been born. So you could never have traveled to the past. This would create paradoxes. And so it's not considered possible. There are also studies that show that any number of dimensions other than 4 that we live in would either result in no life or an unstable universe. If we didn't have at least one dimension of time, nothing would evolve, nothing would change. So life could not exist. So we know we need a time dimension. But what if we had more than 3 large dimensions? As it turns out, it would also likely have fatal consequences. In a 1917 paper, Austrian physicist Paul Ehrenfest showed that if we had even one extra dimension, gravity would fall by a factor of 8 when doubling the distance from a planet to its star. This would cause even the tiniest variation in a planet's orbit to either spiral out of the solar system or meet a fiery death by crashing into the star. Other problems have also been identified. For example, the orbit of the electron in atoms would become unstable.
But
if we had fewer spatial dimensions, then space-time would be too simple for life. For example, if we had only one spatial dimension, then orbits could not form. 2 dimensions would also probably be too simple to result in life. The chart here summarizes these ideas. This leads us to the fact that although this may sound like an anthropic idea, it appears that the space-time has to be composed of exactly 3 spatial dimensions. I'm talking about real, plus 1 time dimension. Because
he's talking about all kind of crazy ideas, but I'm talking about actual, real time and distance where we are relative to where everything else is. And, as soon as you get out of a galaxy, you don't have, gravity drops off exponentially. Let me repeat it. Gravity drops off exponentially. As soon as you get out of a galaxy or any mass or matter, you got no more energy or force or power to slow down time or to contract distance. That's the reason why we can see distant starlight. We can see distant starlight because who knows how many billions of years is going by very fast, because time speeds up and distance is expanded, means it's not actually as far as what they think it is, because every time they want to measure, they try to measure something, They try to measure superluminal motion. They say, okay, no, let's use our measures of distance. Let's measure the superluminal motion 7 times the speed of light, which is not possible, which means your measures of time and distance are off, because you're projecting our measure of time and distance onto a place in outer space which doesn't run at the same time or distance or measure of distance as what we have here. So your measure of time and distance are totally off. You know, I keep on trying to explain this stuff, but these people, these people are supposed to be educated. They go through the best schools and they do all this, study and experimental stuff, and has to be approved and signed off by people who understand astrophysics, and they can't even get measures of time and distance.
Because if it were any different, we wouldn't exist. So count your lucky stars that we happen to live in precisely such a universe. Now, if you watched this video up to this point, you realize that I tried to simplify the concept of space-time by talking about it in the context of special relativity. And as you might guess,
special relativity is totally different, which complicates the matter. It complicates the matter because I'm talking about general relativity, which inside of a galaxy slows down time and contracts distance. But then if the galaxy is moving, or the sun is moving, or we're moving, that slows down time and distance too. I mean, it slows down time and contracts distance too. So you got 4 things to consider: the slowing down of time because of speed, the contraction of distance because of speed, and you got the contraction of distance because of general relativity, because of mass, and you got the slowing down of time because of mass. You got 4 things to consider. I mean, no wonder they think the spiral arms of galaxies are going around too fast, because they're not taking those 4 things into consideration: the speed and the proximity to mass or matter that has mass.
There's a lot more to special relativity. Now, if you want to understand this subject in detail, there's a wonderful course on.
There we go. Okay, we're starting to promote Brilliant. Yeah, I guess that's about it. Anyway, I don't know if that's it or not.
Brilliant.org. Today sponsor.
But anyway, it's nice meeting you, Arvin Ash. I'm sure you're a great guy. I respect, your work, your effort, and your, dedication and everything. I respect all that, But, come on, people. Like, really. This stuff is like real easy. It's real easy when you do the thought experiments. And here we go. I'm going to go here. So here we go. I thank everybody for. I don't know what's going on with my. I can't even see my full screen here. I don't even know what. I did something. I changed. I gotta fix something here. Can I fix this thing here? Size, zoom, 100%. I don't know. Do I make it less? Oh, there it is, right? Is that there? I don't know. There we go. It's a little bit better. Let me go back. 90. Oh. I got to do less than 100% to see this whole screen. Okay, whatever. Anyway. All right. Everybody's been great. And maybe, try to go back and read your comments. I did make Dan Straight moderator because I was watching the video and I just clicked on Dan Straight and made him a moderator. Here we go. I ask questions on videos like this at times, but I either get attacked, or non-answers. Yeah. Oh yeah, yeah. It's yeah. You know, makes no sense. Makes no sense. It just so happens that we live in the correct spot in the universe. Maybe the universe was made for man and was prepared for life, or prepare, and maybe for man, and made for man and was prepared for man. The last created by God. The last created by God as a final act. Mom, this is horrible without glasses. Happens a lot, but it's a double standard. Yep. Well, I mean, it's a little bit annoying and frustrating, and they don't want it, like you said, they don't respond. They don't respond. It's like, oh, just won't respond and pretend like it doesn't exist. That happens a lot, and I'm sure he's a great scientist. He's probably pretty good and everything. With his peers and everything. But let's just review what he said. I said space-time wouldn't exist without matter. Space-time wouldn't exist. So he questioned me without answering to me, and then he answered to me. That's not really. This is a scientist saying that's not what y'all out there. It's a scientist responding, right? So then I respond, and then he comes back with particles have energy with no rest. I'm not talking about anything without mass. I'm talking about what happens because of mass, and that was it. He was gone. He's gone. He just like disappeared into the woodwork, and have this guy go on, talking about something really crazy. Is like he said time cannot be slowed down. And so he's like, wait, I don't know where he's at. I don't even know where he's at. I'm not even gonna read anything else he says. But anyway, that was it. I just, I wanted to make the title like, Jungle Jargon calls out Arvin Ash or something. Well, trying to be nice and everything. Not trying to be mean or anything, but this guy probably is not too dumb or anything, but where's your IQ? Where is your IQ? I mean, I keep asking this. Where's their IQ? It's like evolution is mathematically totally Impossible. Out of the question. Totally out of the question. Where is your IQ? Where are the people with IQ? Where are the people that, with IQ to call out evolutionism or whatever he's trying to, Where are the people with IQ? Where are they? I'm talking about, savant geniuses and all these people with I don't know, what they have, 150, 175 IQ. Why aren't they calling out, why aren't they questioning evolution? And why aren't they explaining general relativity like I just did? Where are the people with IQ? You have to do the thought experiment. You do the thought experiment, and it's so simple. So simple. But anyways, that's enough for right now. I don't want to keep on going and stuff. But I thank everybody for their participation and everything, and I hope to read your comments again soon. Anyways, I've been, when I went to school, it was like 50, 60 years ago, whatever it was. And I'm reading these people in evolution. I'm trying to yell. I'm trying to yell at the book. I'm trying to yell through the book at these people. And of course, nobody's going to hear it, right? So now we have a chance, and these platforms keep, hindering us and putting us down and putting us down and putting us down and everything. Unless we go all out like, Oliver Anthony or something and go just put it all out there and stuff. I don't want to necessarily put it all out there or anything like that. And then you get attention. Once you get attention, then people listen, But for the longest time, they're in the educational system. It's a violation of church and state because they're teaching a baseless belief with no evidence whatsoever and shoving it down the throats of kids in school, in public school, government-funded public schools, right? Which is supposed to be illegal. That's what, you can talk bad about Kid Hovind all you want, right? Yeah. You want to talk bad about Kid Hovind? Yeah. Okay. You can do that all you want, right? But what he's saying is true, is that evolution is not supposed to be government funded. It's not supposed to be government funded. Public schools are government funded. And they're shoving this nonsense, this stupidity, as pseudoscience. Professor Dave, pseudoscience, shoving it down kids' throats. It's nonsense. It's stupidity. It's idiocy. Come up with something better if you can. You never will. God bless everybody. Take care.